Who knows what this is? Okay, good. So a few of you, you're a little bit unsure. It doesn't look very pretty for a visualization paper. If I put the authors on there, you might recognize this. So this is Johnson Schneiderman, IEEE Conference on Visualization, 1991. And as I sort of heard here in the front, this is from the tree map paper. So a space-filling approach to visualization of hierarchical information structures. I think everyone in the room probably has seen a tree map or worked with a tree map. It took a while for these things, obviously, to become popular. And probably also not surprisingly, one of the first applications for this approach was trying to figure out where the big files are on your hard drive, which is sort of a problem that has, I guess, gone away now that we have cloud storage. You don't have to worry so much about what we store. But this is maybe a very classic example from the visualization literature that's also fairly frequently seen in biomedical informatics and biological applications of data visualization. So, as you know, you can use these trees. For example, people have applied them to ontology visualizations and other structured hierarchical data that is somehow associated with quantitative information. Here's another one. And I'm very curious who knows what this is. Does it look familiar to anyone? It's a little. Okay, so I hear splums. Yeah, there's sort of a scatter plot matrix in there. This thing is a lot of worth of money. Let me put on the authors of this paper, Stolte and Hanrahan, IEEE Conference on Information Visualization in 2000. If I put this thing up, does it look familiar? So this is essentially one of the core technologies behind what's now being sold as Tableau. So this is a paper called Polaris, a system for query analysis and visualization of multidimensional relational databases. I find it's quite fascinating to go back in the visualization literature and sort of find these papers. I mean, I've heard about these papers at conferences before, but it's very interesting how it took them, almost 2 decades at this point to turn this into a gigantic money-making machine. I think also a great example how important data visualization has become today. But it's really backed by some serious science that was published in the visualization literature almost 20 years ago. Okay, now I want to move on to this. So this is about visualization of adjacency relations in hierarchical data. Who knows this paper? There are some people in the front who know all these papers. I'm wondering if you've been to a Viz conference. So this is something that most people who use network visualizations today will probably have used or at least seen. And the idea here, the title is a little bit, actually this is part of the title of the paper. I cut away the part that would have revealed what it is. But when I show you this, you probably get a sense of what this technique is called. Going back and forth. You see these edges in this graph visualization form bundles, and that's the idea behind a paper called, and here's another example, a paper called hierarchical edge bundles. So that is a very highly cited InfoVis paper, came out in 2006. As you can see, it has a single author, which is also quite rare. Although I noticed going through these classic papers, there are a lot of 1 or 2 author, maybe a few more author papers in this list of these highly cited Viz papers. So, okay, hierarchical edge bundles, very important for network visualization. Now I want to talk about something slightly differently, and it's called data-driven documents. Who knows what data-driven documents are? Oh, okay, a few, great. So here's an example. I hope this clears it up for everybody else in the room. Maybe not for the ones in the back because it's very small. This is a data-driven document. Let me zoom in a little bit. You now see what a data-driven document is. So data-driven documents, in this example, what this thing does, it turns into this, which you might have seen somewhere if you've ever coded something for a web-based visualization tool. So if you haven't guessed it yet, data-driven documents is what's usually known as D3. So this paper, also published at the IEEE Conference on Information Visualization in 2011, has been cited close to 2,000 times at this point. Again, it's data visualization literature. D3 didn't just, come out of nowhere. If you go back to Jeff Heer's work, I think D3 is probably the third or fourth visualization framework that he created. He also didn't stop with D3. As you know, there are now other things like Vega, Vega Lite, that built on some of this early work, but I think D3 is probably the most popular thing, and I think that most of you will know. Now, so these are some of the examples that I just wanted to point out where maybe you were not aware, or not everyone in the room was aware that there is actually a paper from the visualization community behind these techniques and tools. So I want to talk about two things that are maybe less well known, but I think also quite interesting for data visualization work in biological sciences. So this section is called Diamonds Are a Bioinformatician's Best Friend. I don't really know what that means, but I somehow had to come up with a title for this section. So who has heard about quilts? Not the ones you buy in a, crafting fair. Okay, so two of you have heard about quilts, maybe a couple others who did not dare to raise their hand because this is maybe a little bit controversial. So this is one example for a quilt. Quilts are network visualizations. Typical visualization approach for networks, as you know, are node link diagrams. You probably have heard about adjacency matrices. But quilts are something very interesting. There's also a matrix-based approach, as you can see here. But it essentially deals with the problem that we have too much empty space in most of the adjacency matrices. So this example here is something called genetic quilts. This is a visualization tool for genealogies. Came out in 2010 in InfoVis. And what we see here is sort of a small visualization. This is only a subset, I believe, of the genealogy of Greek gods. But the principle behind this visualization technique is very simple. So I already mentioned they're essentially matrix-based, and they compress away the empty space in the adjacency matrix visualizations. So here's an example for a node link diagram. On the left, you can see different layers have different colors, and we see the same colors over here in the quilt representation. And so essentially you have adjacent layers form orthogonal groupings here in the quilt representation, and the black dots here indicate in this grid indicate the connections directly between the blue and the red layer over here. And if there are any links that go past the adjacent layers, we have them down here below this block. So there are two links from this light blue, there are a lot of light blue ones, from the second light blue node over here down to the purple layer. You can see these going through here. So this is the principle is very straightforward. And the reason why I think this is interesting, and I want to show you a second example from a paper that came out a year later, developing and evaluating quilts for the depiction of large layer graphs. I think for some of you who are working with biological networks, I think this idea that there are layered graphs, and there are a lot of them in biology. For example, gene regulatory networks often have fairly layered structures. This could really be an interesting approach to looking at these kind of networks. So here's a node link diagram. This looks fairly messy when you look at that. Here is the corresponding adjacency matrix. This is a slightly non-standard adjacency matrix. It's called a centered adjacency matrix, where basically if everything that's going down from the top is on this side, and things that are going back from lower layers to higher layers is on this side of the matrix. But you see there's all this empty space. And because it's a layered graph, you see a lot of connections in these parts of the matrix. And now when we switch this over to a quilt, it becomes very compact. Now, as most of these adjacency matrix-based visualizations, tasks like finding a path between two nodes is harder than doing this in a node link diagram. But I believe this is something that has been sort of a little bit underexplored for biological applications, because I think in general, we don't even have a lot of good tools to visualize networks as adjacency matrices. I think we're pretty strong on the node link diagram end of things. But I think there's certainly room for experimentation here to apply this to biological questions. So this is something that I tell my students every year. Look at this visualization approach. Maybe you can come up with something. So far they haven't. So I'm going to tell you now, and hopefully next year we'll see a paper here at BioVis that uses quilts for biological data. I should also point out this is a technique. There's no tool that creates these things that I was able to find or access. Hold on, this is not true. There's actually something to create these Genea quilts, but there's nothing that creates the quilts that are being shown here. At least I couldn't find it. So that's something to keep in mind. All right. Now I want to move on and talk about what I saw last night at the poster session. So I blurred out the title. I don't want to personally reveal anyone's work here, but so what struck me here is a very colorful poster, and of course it drew my attention, not because it's colorful, but because I saw this 5-set Venn diagram in duplicate execution here. So, you know, I think for most of you who are familiar with data visualization, who know a little bit about the basics of how we interpret and really parse a visualization, and can read data back from a visualization, you'll understand that this is not a great visualization. Because if I ask you what is the largest set or intersection in these visualizations, well, what will you do? You will look at all the numbers in there and try to find the largest number, which is a very easy task if I just maybe write them down, order them, and then write maybe the set membership next to that. So it's very hard to even do these simple things like finding the largest intersection in here. And clearly the authors of this poster are not alone in, you know, creating these kind of Venn diagrams that are always very colorful, but very hard to read. So this is the rat genome paper in 2004 in Nature. This is the banana genome paper in 2012, so nothing changed. Just got maybe even more creative. So what this thing shows us here, for example, is the banana genome and orthologs to other or with other genomes. So there's Arabidopsis on there, there's rice on there, I think like palm trees and other things. Well, and again, the same question, you know, well, where's the largest overlap between banana and any other thing? What is the largest area in here? And because all these areas have to essentially be shaped in order to fit this Venn diagram, this is 6 sets in this case, you can't really encode the data in here. And in fact, it's impossible to create, to generally create area proportional Venn diagrams for more than 3 sets. So there's always going to be an issue with the visual encoding of the data. And now this is something that maybe some of you have already seen. So Alex Lex led a project that I was involved in as well in 2014 to come up with an alternative approach to visualize set intersections. And this is called upset. This is a screenshot from the paper. So what does upset do? And it'll get easier as I go along. I to apologize, it's a very dense figure. So here is the actual set visualization. We have sets listed up here, 6 of them. Here, this matrix indicates which sets are intersecting, and then the bars in this bar chart indicate the size of the intersection. Now, because it was an InfoVis paper, this was not really enough to say, let's stop here, because this would be super useful. Because it was an InfoVis paper, we had to sort of explore everything else that we could do. So we also characterize the elements inside these intersections. So, for example, over here, we have some attributes associated with the elements. This is a movie data set, so it has nothing to do with BioVis. But we're looking, for example, at the release date for certain types of movies. And basically, the sets here are different genres of movies, and movies can have multiple genres associated with them. We see average ratings. We see number of times watched and other things. And over here, we went even further. So you can take these attributes and create all sorts of plots. For example, here is scatter plot. I think this is something I can't read. 2 variables mapped against each other. And then you can go in and select different intersections and map them, the colors for those, on top of these plots. You also see down here sort of a list of all the elements in this orange thing, and I honestly don't know what we selected here. There are two things. There's a green one, which you probably can't see from the back, and that's what's visualized here. So you can explore set intersections with this tool, and it was a paper at InfoVis in 2014. Here's another complex example. And that was great. So people liked it a lot. Because I think it's easy to see the challenges with Venn diagrams when you visualize set intersections, which are very common in biology. Well, So we had this great tool, and so it's a web-based tool. The software is available. It's on GitHub. You can go to the website down there and you can play around with it right now. But in order to get the data in, you sort of had to put the data file somewhere in a Dropbox file because we didn't want to implement a full-blown server and then link it. It was all very messy. Some people managed, but then they got these beautiful, complex things here, and they wanted just something to put in their paper. And that was sort of a common, in my opinion, a fairly common thing that happens with Viz papers. They're generally very you look at all these different things that could be done, and then of course you have to build this prototype to demo them for the paper. But for most applications, about 20% of all the features you put into this tool are sufficient. So that's why we went back and looked at this problem where we don't have any attributes associated with these orthologs here. We just have the numbers, and for that you can just create a simple upset plot like this. So what we did, we created an R package, because that's where most people, or a lot of people, will generate their plots for papers, because that's where they have the data. So here I think I'll recommend you have a look at the paper. It's very straightforward. The question like which is the largest intersection is very easy to see. Just look for the highest bar over here. It's where all 6 species intersect, but we see there's another high peak of many many elements that are shared, many orthologs that are shared between species, and you can see this is a subset of 3 different species. Over here, I think these are the date plants, no, different types of rice, actually, that are related to each other, and they share a lot of orthologs. So with this R package, we really were able to satisfy a lot of interested users in this technique. And it has gained quite a lot of followers. Someone implemented a Python-based version of this approach, and we've seen this pop up in all sorts of papers in the last year or so. So this is the R package paper. All right, now I want to go on and dig a little deeper. So here are 2 examples of some visualization techniques that you might not have heard of that might be useful for your work. In particular, if you're thinking about building new visualization applications. So let's dig a little bit deeper. Where can you find more? Because this is sort of where time will be limited today. But luckily, people in the Viz community are great at summarizing, state-of-the-art work. So there's something called state-of-the-art reports, or STARs. Other communities that I know just call them reviews. But these are STARs, and just a euphemism for a review paper. And they're excellent because they are presented at BioVis generally, and then they're published in this Computer Graphics Forum. The one thing that's maybe not so excellent is that maybe not every library subscribes to that journal, and there are not a lot of open access papers there. So you might want to search around a little bit to find those papers elsewhere. Okay. So there's a very nice website put together by Professor Min Chen from Oxford University. He lists all these STAR reports that came out in the last couple of years. The URL is down here, and of course I'll share my slides with you after the talk. So you can click on that link or just Google for Min Chen, Oxford, and STAR reports. And here are a couple of examples that I want to share with you. So what has come out in the last couple of years? There's a lot of literature on graphs, a taxonomy and survey of dynamic graph visualization from last year, a visualization group structures in graph, very common task in visualization of biological networks, visual analysis of large graphs. That was from 2011, so there were probably some updates in the more recent ones. They have 2 on tabular data, matrix reordering methods, also for tables and networks, and then visualization of multivariate scientific data. All of them great resources if you're thinking about creating a new tool that falls into any of these categories. There's also one on set visualization. And there are even more. So there's one on imaging, visualization of live cell imaging data, molecular structures, one in general and one on biomolecular cavities. So check these things out before you start implementing your own thing. Of course, also search the biology literature because there will be probably a lot of other reviews that overlap very little with those. So that's, I think, one of the general problems that I want to point at later. There are also 2 general ones that might be interesting to this community, one on web-based visualization, one on integrating machine learning and visual analytics. Now, that's not all. So many of these review papers or STAR reports come with a website that looks something like this, where someone collects all these visualizations. It's a great thing about visualization. It's very pretty, at least to look at, maybe not necessarily to use, where there are usually some sort of lightweight taxonomies that they use to organize the content of these repositories. And then you have all these thumbnails with links to the papers, etc. So if you are trying to invent something new, you might want to go to these websites. There's one for trees, There is one for time visualization. There is one for set visualization. And you'll notice there's sort of a cottage industry of these. Like there's dynamic graph visualization. These things all look all the same. There is one for high-dimensional data visualization. And believe it or not, there is one on surveys. So there's one, just a survey of surveys, if you like meta-analysis. So all of these are available. Now, these collections generally don't judge at all whether the techniques are good or bad. If you're interested in something that is a little more data-driven to tell you what you should be looking at maybe. Now, this is not as well organized, but very, very interesting. Something that I find quite useful in preparing this talk is this thing called InfoVis citations. So it's a visualization project visualizing literature citations in the information visualization community. In fact, these are only papers published at the InfoVis conference, but you can see here for every single year which papers, this is a list of all the papers. The darker the color, the more highly cited. Guess which one this is, 2011, you remember? E3, exactly. And there are a couple of other nice ones. Down here, 1995 is a text visualization approach. I don't know if this is Polaris or not. In 2000, 2006, the one with the yellow dots on the inside are the best papers. So this was Danny Holton's hierarchical edge bundling. 2008 is this is a multivariate scatter plot visualization and exploration tool, also very interesting. This is Upset up here in 2014. Was not the best paper, unfortunately. So anyway, check this out. Very, very useful. Okay, now, in addition to all these techniques, the visualization community also has something much, much better to offer, in my opinion. And now, the sad thing is I don't have time to tell you in detail about this, but I think our community here, and I say our community is the bioinformatics community, people who are doing data visualization in this, at ISMB basically. Where we really can learn a lot is when it comes to methods, visualization research methods. So even though Kai is a great teacher, she didn't teach me anything about data visualization research methods. Neither did any of the other people that I've ever come across, whether it was at the University of Cambridge or at Harvard, teach me anything really about visualization research methods. So maybe I didn't take the right classes, but there's a lot of very interesting literature on evaluation techniques, for example, something that I think BioVis really needs to figure out. Some of us are doing a fairly good job on that, but not everyone does that. Design methodology. How do I go about creating a visualization tool, right? It's not just rendering some data necessarily. Task taxonomies, very helpful when you try to understand what a user might want to do with your visualization. There's some great papers. There's one from 2005, John Stasko, low-level tasks for data visualization, tells you everything what a basic visualization needs to support. I didn't include it today because time is a little bit limited, but very, very important stuff. And many more things that you can learn from the VIS community about how to go about creating visualization tools. If you're really interested in this topic, there is a series of workshops called Believe that cover these topics. There will be one this year in the fall at the IEEE VIS conference in Berlin. So there's something, if you care about this, you might want to check this out. All right, so I'm running a little out of time, but I want to still go into this. So this is called Diamonds in the Rough. And this is where I'm going to talk about what makes a good BioVis tool. Well, clearly, you have to have great data visualization. But it's not all, right? So what you get from a lot of papers published in the visualization literature is great data visualization. There are even some great design study papers describing visual analytics or visualization tools for biological data. There are some on genome, assembly visualization, synteny visualization, networks. It's all out there. But you probably have never heard of those tools because they were just great at visualization. They were lacking something. And so there are some other parts that, in my opinion, make a DataVis tool good and useful, such as usability and user experience, which is not the same thing necessarily as visualization research. So I can say that because I certainly have produced some visualization papers that were good visualizations, but terrible at usability and user experience. And finally, there's a third piece, really, really important for tools used for data analysis, is integration with the ecosystem. So you don't want to have your own standard or own special format for the data that goes in, right? You want to be able to feed in whatever the standard is in the field for which you're having data, right? Whether it's a bed file or a BAM file, you don't want to have your own format for that. You want to be able to maybe send some data from or embed your visualization tool into a pipeline, et cetera. So all of those things together, in my opinion, make a good BioVis tool. And that's not necessarily what you're going to get out of a Viz research project, right? So this is where we want to be. And I think there are some things that generally are lacking when you just look at the visualization research. So this is, the reason why we have so few, and I'm trying to explain this, and I'm not sure if I can do this. So this is very preliminary work in a way. It's a discussion from a seminar at the Dachschel Castle in Germany that we had in April. And so one of the questions that we discussed is actually collaboration between visualization researchers, biologists, and bioinformaticians. And it's a little hard to see probably. I thank Michael for drawing this. And I just plugged this in here because I think this is a really interesting thing that I wanted to emphasize. So what we're looking at is a time axis down here. And here is a value axis, cumulative value. I can't really tell you what exactly I mean by that, but I'll try to explain it. So nobody really can yet explain what exactly it means, but I think I'm going to get the message across. So when you're a Viz researcher, you're on this blue line here. Oh, sorry. You're on this blue line, which sort of increases very quickly up here up front. And this is where the visualization paper is published. So you have a collaboration, you're working together on a project. So the first thing, you build this prototype, you write the visualization paper because, of course, there's an InfoVis conference or a Viz conference every year, so you've got to get that done. Ideally within a year. And so then you're at the peak, right? This is when you as a Viz researcher get your maximum value out of that project, more or less, okay? But for the BioVis person or the bioinformatician, right, this is not really where you get a lot of value. If you have a prototype, well, who's going to use it or cite it really? Very rarely. What we want in BioVis, I think we want tools, right? And to build a tool from a prototype is usually, more time, right? It takes more time because you need to add support for, loading the data in, for actually making it useful, strip out all the things that the Viz person included because it sort of was part of the design space exploration, but is maybe not needed really. So this is the problem, right? So here is the Viz researcher gaining a lot of value, and here is the bioinformatics person gaining value. And this thing in between is what we call the valley of death. It's where a lot of these projects die because they're simply not useful as prototypes, right? You want a proper tool. And, for the biologists, they actually can gain value anywhere along the way, right? If they're lucky, they look at the prototype and, that's just where they see the pattern they were looking for. But maybe, as a bioinformatician, you probably have to wait for a while until this tool is out there and you can publish on the tool and actually people start using and citing it. So I thought that people might fall asleep, so it's time to wake up. I just wanted to, I don't know if that happened. What can you do about all of this? So I just want to very briefly wrap up here. So what can you do? Number one, right, become more aware of the visualization literature. That means search outside of PubMed. I mean, everyone is using Google these days, I presume, but just in case, you're not going to find all the visualization literature in PubMed. Attend the Data Visualization Conference. So IEEE Viz in Berlin will be fantastic. There will be a BioVis Challenge workshop. I'll tell you more about that later, I think. When I first went to a Viz conference about 11, 12 years ago, it was absolutely eye-opening. My mind was blown, literally. And I think we wouldn't have, I don't want to read too much into that, but I met a lot of people at Viz conferences who had shared interests in biology and data visualization. And I think, because we went to Viz and talked to each other there, things like BioVis started to happen. And I think Viz is always a great community and it's a fascinating conference. When you plan a collaboration, right, keep in mind that the Viz researcher might not build that tool for you, might not build a tool for your users. So, request resources for software engineering to harden that at least to the point where people can start using it. Think about usability and user experience independently of the visualization. And finally, when you write a bioinformatics visualization paper, describe your design approach. Not just write, it doesn't fall out of the sky how you came up with your design. This is how most papers, unfortunately, are written about visualization in bioinformatics. You can certainly describe how you figured out what your users need. That is part of the research in data visualization. I would love to see more of that in journals like Bioinformatics and Nature Methods and where else you're publishing your research. So with that, thank you very much.
Yes, thanks very much, Nils. That was very, very interesting, and I hope we can at least answer a couple of questions. So please come forward who wants to ask a question. But before, I would actually like to apologize. When I introduced Nils, I should have actually mentioned, indirectly hinted at that. I should have mentioned that it's actually due to Nils that we have BioVis. So I think we should actually keep that in mind.
I was not trying to say that.
I know. So you said that differently. And yeah, fair enough. That's definitely true. So anyway, who has a question for Nils? Please go ahead and go to the microphone. Thanks.
So hi Nils, this is Daniel.
Hi.
It's a very interesting talk. I like the examples and basically also the fact that some of the journals are not found in Medline. I was not aware of this. With respect to the visualizations, there are many visualizations that are much better than the visualizations that are currently used. And I work in a pharmaceutical company, and the issue I see is often that people, my colleagues, are used to a certain type of visualization. As soon as I introduce a new visualization, they're like stuck and say, "Ooh, what is this now? Yeah? This is not a Venn diagram, I know a Venn diagram, but what is upset? What is now happening? Yeah? What is this?" So they're used to a specific type of visualization, and it takes a certain amount of time to explain them, okay, this might be better, because you see the things you want to see more easily. Right. And I think, yeah, this is some step one has to consider.
I agree. And I think this is a very important task also for this community, right? I think besides building visualization tools and visualization techniques for biomedical research, I think there's a lot of need for education. And this is not anybody's fault that people don't get visualization education as they, go through someone, who was this, Martin, like kindergarten, preschool, et cetera, elementary school, high school, college, grad school, and they still don't know anything about data visualization. I think, but that's where, thinking about how to educate my colleagues is also very important, right? I mean, it doesn't have to be forced, but I think most people really appreciate these opportunities to learn something about visualization, because the nice thing about visualization, unlike, in my opinion, say statistics, is you can see what's going on, right? And I think people appreciate that when you explain a visualization to them, and you can easily ask them to compare. So, find the largest intersection in this Venn diagram and look at this upset plot, for example. I think that's an opportunity that shouldn't be missed to help people, wrap their head around how visualization actually works.
So maybe to come back to this, I would actually comment that what can we do from BioVis? We should, and that's what we are working on, trying to at least develop a curriculum for universities. We didn't start with kindergarten. Maybe we should have.
We should.
Yeah. So, is there more questions? Okay. So everybody is really happy with your talk and all the questions. So thanks again.
Thank you.